Thanks, everyone. Thank you for being here. Before we begin, just a short disclaimer that these are the views and opinions of myself and Dan. This does not represent the views of Intel. And as I said, my name is Trikalinou. I hold a PhD in computer security from Wright State University, and I currently work as a research scientist in Intel Labs, working on various security-related projects that are going to be featured in Intel's new products. And here is Dan.
Hello, I'm Dan Lake. I also work in Intel Labs with Anna. I have a bachelor's degree in electrical engineering and physics and a master's in computer science. I work in a team within Intel Labs called the System Prototyping Lab, and I build hardware and software prototypes to help researchers such as Anna test out their ideas.
So what should you expect from this talk? This talk will describe some early research that we have been doing, and that is regarding a physical attack on DRAM memory. We will describe two limitations that might result in a vulnerability, and that is, one of them is for hardware design for DRAM, and the other one is a protocol limitation. And just to be clear, we haven't launched a successful attack yet. We are in the process of doing that. We have completed most of the steps. We have still a little bit to go. So if the final result is successful, then the result will be a full DMA access to the entire physical memory. And because this is a hardware design and protocol limitation, that is applicable to all memories and all architectures. But before that, let's say a few things on what is DMA attacks in general. So DMA attacks are types of physical attacks where the attacker connects to a DMA-capable port, such as a PCIe or a FireWire, and through that, he's able to gain full read-write access to the entire physical memory. So the goal of the attacker is typically either to read stuff from memory and extract secrets that are held there, such as a disk encryption key, and through that unlock the disk, or corrupt the memory in some way in order to bypass the platform security policies. An example with that would be to modify the page tables so that an application that was running at ring 3 permissions is now running as ring 0. And an example of an actual DMA attack is one that was presented or disclosed by Ulf Risk in 2016 on a MacBook Air. He described a vulnerability that allowed a DMA attack, and through that he was able to obtain the file vault disk encryption password for that MacBook Air. Just to be clear, this vulnerability has been patched in macOS, that version, in December 2016. So what are the advantages of launching such an attack? First of all, the hardware, in order to do it, is kind of easy to get, and it costs less than $300. And also, there is already available software online. And finally, there's also great tutorials by many people that are actually in the room here with us on how to do that. On the flip side, it does require this specific interface. You need to have this PCIe port or this FireWire port in order to connect to that and do the attack. And there are also ways to mitigate that. And specifically in latest systems, there have had some BIOS settings that limit of what you can do with DMA. And that is either through BIOS or by setting up the VTD accordingly. And it can also be mitigated by blocking associated drivers that allow to map what the DMA device can do to the actual physical memory. And you can also block the specific port. So if you have a system and you know that, hey, you're never going to use that port, you can just block it. So the motivation for our attack is, what if we could eliminate all these disadvantages? And in order to understand how we're going to do that, we need to understand a little bit of how the DRAM is designed. So just basic information, the DIMM consists of a series of DRAM chips that are mounted into the PCB. And this DIMM is then inserted into the DIMM socket that is mounted onto the motherboard, and through internal traces or internal wires, this DIMM communicates with the processor. And here is how it looks on an actual system. This is just a reference system. And it has a current generation motherboard and CPU. And as you can see, it has one DIMM, and there are a few available empty DIMM slots. But if we let's take a closer look into that. The green part is again the DIMM PCB that is inserted into the system, and the black thing underneath is just the nearby empty DIMM socket. But what is interesting is the tiny silver dots that are there. I don't know if it's clear. I don't know if they are clear on the PowerPoint, but those are the actual DIMM pins that make the connection between the DIMM and the system. And again, if we flip the same system on the back side, we can see those same pins there that are present there as well. So overall, the hardware design characteristic that we found is that all 288 pins of each of the DIMM sockets are exposed on both sides of the motherboard. And those pins are also electrically connected. So basically what it means is if you have a working system that the processor is doing reads and writes to the memory, if you can attach to those pins, then you can observe that communication. You can read stuff from there. And I would also like to point out this is a standard OEM design. This is not something that is specific to that board. But the question that we raised is how could we exploit that in a little bit more sophisticated way? And specifically, what if we could plug into those pins and just request normal reads and writes just as the processor would, but be able to impersonate that through something else, through, say, a memory controller that the attacker has. But in order to understand how that would work, we need to see a little bit of how the DRAM actually works. And this is something that is being specified by the JEDEC standard. And that defines the set of requirements that must be satisfied by all memory modules and all architectures. So the first thing that happens when you first boot up your system is that the CPU will read a specific portion of the DIMM that it's called Serial Presence Detect, EEPROM, and that holds information that is programmed by the manufacturer of the DIMM, and it contains what is the DIMM's module serial, what is the support edge voltage that it operates on, what are the minimum latencies it operates on, etc. And this is done through the SM bus. Next, the CPU, by reading this information, it will decide on some clock frequency that he wants to use, and it will configure the memory controller accordingly. The next step is the memory controller performs a task that is called memory calibration. And that is because the memory controller is agnostic of the motherboard it sits on and the DIMM it communicates on. And that makes sense because you want a system to work with different kind of DIMMs, and you want the DIMMs to work on different kind of systems. But those all have different characteristics. So in order to do that smoothly, the memory controller is responsible for calculating what is the round trip time between the time that it issues, let's say, a read request to the DIMM to the time that the data came back from the DIMM. And another thing that the memory controller needs to do is to calculate small discrepancies between the different traces. So as I said, the DIMM has, DDR4 have 288 wires or traces, but those might have slight discrepancies. So one might be a little bit longer than the other one. So the memory controller needs to account for that. And the final step of the initialization is that the memory controller needs to set the DIMM's mode registers. Those are registers that are held on the DIMM, And they're used in order to enable or disable features or to fine-tune some of the timings. So if you, say, want to overclock your system, those are what the registers that you need to poke at or let BIOS do it for you. Next is what happens when the system is in normal operation. So obviously the CPU will constantly request for reads and writes, and it will send them to the memory controller, which is then responsible for scheduling them and optimizing the memory access, and then receiving the data back and go back to the CPU. And also, the memory controller is responsible for scheduling periodic memory refreshes, because the way that the data are held in the DIMM is by having a small electric charge in the capacitors that are on the chips there. But this charge leaks over time, so the memory controller needs to do refreshes in order to actually keep the contents of the memory there. The other state that is actually pretty interesting for our attack is what happened during sleep, and specifically S3 sleep. This is also called suspend to RAM. This is a power state where the contents of the memory are preserved, but the CPU is powered off, the memory controller is powered off, and the memory controller, the only thing that it does is that one specific signal, the clock-enabled signal, needs to be 0, and the rest of the signals are in tri-state. And during that state, the DIMM is in self-refresh state, so it's responsible for keeping the contents there by itself. And the moment that this clock-enabled signal goes to 1, then the DIMM wakes up, and then you can issue reads and writes again. And by waking up of the S0, again, the CPU and the memory controller is powered on, and now, and only now, you can do reads and writes again. So overall, the protocol limitation that we have identified is that really there's no state information that is held on the DIMM. Everything is held on the memory controller side. So the calibration results, the clock frequency, all of them are stored in the memory controller. And the other most important thing is that there's really no authentication between the memory controller and the DIMM. So really nothing prevents an attacker from impersonating a memory controller to the DIMM. But how could we exploit that? What we are thinking is to create a device that is attached to those exposed signal pins that I showed you earlier and impersonate a memory controller to the DDR. However, that would be extremely difficult when the system is in S0, normal operation, because the victim system memory controller will issue reads and writes, and the rogue memory controller or the attacker's memory controller will need to intercept that, and it will be a mess, and it's going to be extremely hard. However, it would be possible when the system is in S3 sleep, because then nobody talks to the DDR, and the rogue memory controller could be the sole owner of that DDR. And an actual example that we thought of how this attack would be practical is, say, a victim goes to a conference or a Black Hat conference and leaves their system in S3 sleep. Then the attacker could get hold of this system, attach the rogue MC system or attacker's board to that exposed pins, and now the attacker would own the system. And here are the steps that we have identified for launching a successful exploitation. First of all, as I said, the attacker needs to attach the rogue MC to the victim system while the system is in S3 sleep. Then the attacker will need to pull the clock-enabled signal from 0 to 1 in order to wake up the DIMM, do the calibration, because we are introducing new traces, and our rogue memory controller needs to account for all those signals, new signals that we are adding. Then we obviously need to do memory reads and writes, because there's no DMA without that. Then the attacker needs to pull the CKE to 0 in order to put the DIMM to sleep. And finally, the attacker would detach from the victim system and let the system wake up normally. And in that state, the system would accept whatever modification we have made to the DIMM as he has made it, as the system made it itself. And next, we're going to go through each one of those points, and Dan will take it from here.
Great. Thank you, Anna. So what I'm going to talk about a bit is some of the lab work that we did and some of the hardware design work that we've done to approach this attack. And I'd also like to start by saying that although we do work for Intel, none of the information that we used for this attack was internal. This is all things that we did in the lab using the system that Anna showed earlier. So what we found to start our attack was we had read through the JEDEC specification about how we expected the memory to work, and we took our system into the lab and essentially went through validating our assumptions about how the DIMM worked, as Anna had just described. So we went through each one of the 288 pins on the bus and tested out what was the logic state and what was active and not active on that pin, both during S0 and the S3 state, which we were most interested in. And we did find out and confirm that all of the signal pins were in a tri-state mode except for the CKE signal, which is part of the self-refresh exit command that the memory controller would require, would issue to the DIMM to wake it up. So the CKE signal being part of the self-refresh exit, we needed to be able to control that signal to be successful with our attack. So the first thing we did with that was we measured the signal, and we found that it was being tied by the memory controller to a low or ground state. Even while the memory controller was off, all the rest of its outputs were disabled, that CKE signal was tied to ground. So in order to overcome that, we don't want to just tie 1.2 volts, which is the DDR4 voltage level, directly to that CKE pin, because it's never a good idea to short power and ground together. So we decided to test out a variety of resistors. I'm showing here in this diagram, we call this the attacker's resistor, RA there. And we tried a bunch of different values to essentially measure what is the internal resistance to ground for the memory controller, and how much current do we need to apply to this pin in order to overcome the internal pull down. So the goal there was for DDR4 is about 0.7 volts. It's just over half of the voltage rail for DDR4 is where we needed to get to. And again, we wanted to pick the largest resistor value we could so that we don't damage our memory controller when we do this. So this is a picture of my lab bench. You can see here I've got my power supply and a meter. Not shown here is like the mixed domain oscilloscope that we use for measuring the clocks and other differential signals. But we went through each one of the signals with this little blue probe wire here, and this was how we probed all the signals to test. For each signal, when the memory controller is asleep, are we able to assert that signal into a 0 state? Are we able to assert the signal into a 1 state? And we validated we could do this for all signals except for the CKE, which requires this additional boost and resistance to protect the memory controller. For our particular system here, we found a safe value was around 50 ohms. We did test other motherboards, and this would be different for different DIMMs, different motherboards, different processors, but it was around 50 ohms was a safe value to get to where we needed to do. So the other thing that was mentioned was calibration. Again, this is where we connect this is a requirement for any memory controller attaching to a DIMM, is it needs to have, it's not so much of a handshake per se, but they do send some bits back and forth to measure round trip times and essentially calibrate that the data and the clock are aligned for successful reads and writes. They try to form an eye where your data is aligned right in the middle of your clock window. So that's part of the purpose of the calibration. Now this normally happens on your desktop system. Every time you boot up, it calibrates the memory controller against whatever motherboard you're using and against whatever DIMMs. It's what makes all these parts interchangeable. But we actually found in the JEDEC spec, there's nothing that prohibits us from doing a calibration at any time, even while the system is on. The system is in S3 sleep, and we can just come in with another memory controller and request a new calibration. It doesn't affect the data that's stored in the DIMM at that time, and it allows us to calibrate our memory controller against the DIMM that's already in the system. We also expect that the calibration results repeated over and over on the same system are the same, or at least close enough, given that the traces haven't changed length, temperatures haven't changed significantly between run to run, that this is repeatable on the same system. It may give us the ability to pre-calibrate for a known victim system if there's a particular laptop or server that you're interested in targeting. It's possible potentially to calibrate against that before going into the attack. So the next thing that we want to do to make our attack easier is to adjust the clock frequency. The default minimum clock rate for DDR4 is 800 megahertz. It's not an extreme clock rate, but it's pretty brisk. So normally DDR4, in order to ensure safe or reliable operation at that speed, includes a delay lock loop. This is a circuit that's in the DIMM chips themselves, and it's normally on, and it allows again, the alignment of the data and the clock within each of the DIMMs when they're sending and receiving. So what we'd like to do is reduce that clock speed to something slower that's going to make for a more reliable connection, given that we're not really designed for that system. We're just kind of attaching ourselves onto it. And the way that we need to do that to reduce the frequency is to disable that delay lock loop circuitry that I mentioned. Luckily for us, that's a feature of the DDR4 spec, is we can turn off that delay lock loop in the cases where it has been implemented by the DIMM designer. We do that by writing to one of the mode registers that Anna mentioned. So we, right after the calibration, we can write to the mode register disabling the delay lock loop, and then when we wake up the DIMM, we can essentially use any clock frequency we want as long as we're maintaining the refresh interval required so that the data stays fresh in the DIMM. We found that to be about 128 megahertz for the particular setup that we're using, which sounds a lot better than 800 megahertz. So those mode registers, again, there's no protection on that. Anybody can read and write the mode registers. And as long as we set it back to the value that we found it in when we're done, then the host system won't know that we are on there using a different clock and different register settings. So finally, we want to issue reads and writes. This is where we actually can read the data. And here we're not doing anything tricky. We're just following the JEDEC specification for how reads and writes are conducted. If you've seen the spec, it's many bubbles in a state diagram with all sorts of conditionals. So we didn't put that on here, but essentially the reads and writes will be used to scan through all of the memory. We can essentially copy all the memory out at that location. That's the idea. Then we can selectively write back to the memory of interest, maybe once we've evaluated what's there, or maybe we want to corrupt some data or change a key. That's the goal there. So what we're using is an FPGA using an off-the-shelf memory controller IP block. Again, this is not proprietary things. These are all things that we just use that were available on the market. So this is a picture of the hardware that I've built. Anna and I worked on this hardware over the last, I'd say, 4 months or so, building this out. So I've built multiple of these boards. Again, we're using an FPGA, and you can see at the top there that there's a DDR4, what we call a footprint on the PCB. This is where a DDR4 connector can normally be installed. So I did build some of these that have a connector. We've been able to put in DDR4 modules into those and test out that our circuit board works, our FPGA code works, we're able to read and write, and then we've brought this board into the lab and tested that our signals are acting the same way as our victim system. So the next step that we're doing now is this board here. You can see there's no DDR4 connector, it's just these holes. These are pretty small holes. If you've seen one of these before, they're about 0.5 millimeter in diameter and 1.7 millimeters apart. So what I'm building right now is a mechanical interposer connector. This is a piece that's built out from 288 spring probes that connect into the holes that you see here on the previous slide. So those spring probes connect into these. They get soldered in place. And the tops of them each have one of these crown tips that connect onto those exposed pins that we showed on the back side of the motherboard. So again, once we complete this step, we will be able to attack the entire bus rather than just attacking individual pins on the victim motherboard.
So yeah, this is where we're at right now. And here's the threat model that we have for this type of attack. First of all, it does require a skilled hardware attacker in order to launch it. It was definitely not easy to build one of those boards. It was not easy to build the connector. And in order to make the attachment to, it will be a little bit tricky. Then it will obviously requires physical access, and it's invasive in terms that you will need to dig out the motherboard that you're going to attack. If it's a desktop or if it's a server, it might mean that you need to take the back panel of the tower off and attach this device. But if it's a laptop, then you really need to open it up and get access to the DDR pins. And because of that, it does require some time to conduct. So it's not an attack that you can complete in 5 minutes. And finally, it requires some prior knowledge on the victim system that you're planning to attack in order to do the calibration beforehand and reuse it for the actual system that you want to attack. And another thing is that, as we said, the mode registers, those can be set to default, in which case it makes the attack possible. But if they're not set to default, if, say, someone wants to overclock their system, then it will be a little bit trickier for our attack to be possible. So, as we said, we are currently working on completing the mechanical connector and running the attack on the full length of the bus. And we anticipate that the only gating issue that will say that, hey, this attack is not possible, is the signal noise. Because we are attaching extra wires, and this connector that we have, even though it has the crown tips and it will be the best that we can, it might add so much noise that the signals are not clear enough in order to make reliable reads and writes. That is the only thing that might prove that this attack is actually not possible. However, we do have some ideas on how to solve that, and one of them is through making the clock frequency, the clock run slower, because even if we have a little bit of noise, it won't matter that much if the clock is slow enough. So what can you do in order to protect against this type of attack? Well, first of all, it's always a good idea to focus on physical security and not leave a system that you really care about and, well, anywhere. just care about it. And the other thing is that you can use Hibernate instead. So in that state, the contents of the memory are not preserved instead of the S3 suspend to RAM state. And as a long-term solution, we were thinking that it would be a good idea to change the DIMM socket and the motherboard design so that those pins are not accessible. So even if our attack might prove not to be possible, you're still exposing some information there because you can read the signals out and you can get information from that. And in the other mitigation that we have thought is to add some kind of authentication in the JADEC spec, so the DIMM will not blindly trust the memory control, whatever memory controller is trying to communicate with it. So to conclude this talk, we described some early research that we have done into a new physical attack for DRAM memory. It does require a skilled attacker, and we did the attack, or we're trying to do the attack by exploiting a hardware design and a protocol limitation. This is a new line of research for physical security. We were just trying to explore what can someone do if they have physical access to a system, and really test the limits of that. And as we described, there are short-term and long-term mitigations. So with that, thank you for being here. My team is hiring too, if you're interested in working on cool new security projects. Questions? Yes.
So the question was about, can this be applied to laptops where the chips are soldered onto the board? So there's a variety of different ways that can be done. A lot of times laptops, maybe not like the newest, like ultrabook thin ones, but a lot of times they'll use SO-DIMMs, which use a surface mount component rather than a through-hole component. If it's an SO-DIMM with a slot, they still, we've noticed, do have these little pins next to the DIMM, and we've envisioned creating a device that could be essentially slid into that socket next to the DIMM. If it's using something like a BGA device where it's soldered directly on and all the pins are underneath, that would probably be, from my estimation, much safer. I can't imagine how you would get under there. Without modifying the board. Certainly, like within our lab, we do remove components, put an interposer piece in, and then put the chips back on it, but that's now quite a big undertaking to build a device like that.
What would you estimate the cost to produce the hardware? Like if you made a kit for other people, you've done the legwork and figured it out and trial and error to do it, but at the end, now that you know the hardware required, what would be the cost of material to then mass produce or share with others?
We do have the cost ideas from building the board that I built in-house, but it probably wouldn't be a good estimation for production. So I'd have to say, as working in a prototyping lab, I never build more than maybe 100 of something. So I don't really have good estimates for, I mean, I could tell you this board cost 1,000 or 5,000 or 10,000, but it doesn't give you a good idea of what it would be in volume, and I don't have the experience with mass production to know what the potential cost would be.
Well, what is the cost of the board you did produce?
I don't think I can really say. It was thousands.
Okay.
So I think the question in the back was, have we thought about open sourcing the board design? I think I don't think we would be giving out per se a recipe to do this, but yeah, I think once we have the successful attack, then we would be prepared to provide more details about it, but I don't see a recipe coming out. But that's really Anna's area. It's her research.
Have you started the work to influence the JEDEC spec yet?
Do you know?
Not yet, because we don't have an actual attack yet, right? So I think we are gonna start doing that slowly and really, get going on that when we actually have something on hand. I think that makes sense then.
Yeah, that's just a time-consuming process.
You know best.
So hi, for this it looks like you have a single DIMM. Motherboards are more complicated than that, right? There's multi-DIMMs and there's also dual channel. Have you considered that, and what is your approach for that?
I don't think that will be a real issue. It's just a matter of scale. If it's possible in 1, then it's possible in 2, in 4, and more than that.
Okay, so for multiple DIMMs, if your address is spanning across DIMMs, how would you address the memory space, since you're attaching to a single DIMM?
Okay, so the question is more about how the physical mapping versus memory, physical address versus memory addresses happen, right? That really depends on the system that you're using, the processor, the generation, even the DIMM that you're using. It's not straightforward, but it's proprietary too. However, I believe that there is some work done in that area.
Okay.
There's a question up front. Somebody had a hand up.
Yeah.
Hello. I'm wondering if you have evaluated whether this attack could be thwarted by encrypted RAM, or if it would still somehow be possible?
Yes, we have thought about that. So the idea of the attack or the attack vector will still hold, right? Because you'll still be able to read and you'll still be able to write or corrupt the memory contents. Now, it's just a matter of what you're trying to do and what is the system you're using. How is the encryption being done? Is there a turn off switch for that encryption? It really depends. However, I can answer that if you were trying to do this attack into SGX protected memory, then the attack will be detected right away, because there's both encryption, integrity, and replay protection.
Okay, thank you.
Yeah.
Hi. Kind of in alignment with encryption, I know a lot of memory controllers also have some kind of scrambling, not necessarily for security, but for noise avoidance. Mm-hmm. Would you imagine you run into any of those issues, or have you run into those issues where if you write the data from the system, it may not appear correct if you look at it from a different system that doesn't pull it through the same memory controller?
Yes, we have thought about that. However, this is, as you said, this is not something that was done for security. Mm-hmm. We haven't figured it out exactly how we're going to solve it, because we're not there yet, but we still have access to all the memory contents. Now it's just piecing them the right way, right?
LSR or whatever. Okay. Cool. Thank you.
Thank you.
Have you thought about actually reading the memory as it's going across the bus when it's in S0 mode? And I noticed you said authentication on the JEDEC spec. Have you thought about confidentiality as well?
I can speak to that. I think in terms of reading the memory, especially if you're talking about a system that's been compromised, like in a data center where somebody has full-time physical access to the thing, there's currently a variety of off-the-shelf memory interposers and taps that have isolation resistance that allow you to sniff the bus readily. I mean, those are products you can essentially buy for that. What's novel here is being able to modify the contents undetected by the system. None of those interposers allow you to actually inject data into it.
Okay.
Did that answer your question?
Do you think it'd be possible to use an unpopulated DIMM socket to read and write data in another DIMM socket?
So that's a great question. We did explore that, and depending, like the other gentleman's question about whether you're using single channel or dual channel, and the layout of the motherboard, UDIMMs, RDIMMs, LRDIMMs, different technologies have different layouts of the signals between the different pins or different sockets. But there aren't any of them that we found that allow us to access all of the signals that we need from an adjacent socket. In other words, there isn't any signal that goes directly from the memory controller to all of them. They have different address lines, or they have different clock enable pins, various things like that. So that would be very handy to be able to plug into a different socket. Thanks for the question. Yes. The question was about freezing the RAM to get lower clock speeds. So the question was about freezing the RAM to get lower clock speed. That potentially could work. So I had mentioned earlier that the lowest clock speed we could achieve while maintaining the JEDEC specification requirement for refresh was 128 megahertz. So to lower it than that would violate the JEDEC spec, could potentially risk data corruption. But again, using something like a freeze spray, we could risk going to an arbitrarily low frequency. It's just we're not then guaranteeing that the memory is refreshed at the phase that it requires.
So you mentioned that it potentially requires a specific knowledge of the target machine. Just how specific do you think the knowledge you require?
The only data in the that would be specific to that system that I think we may need to know would be about if the BIOS had set specific mode registers in the DIMM that we weren't aware of. And the mitigation to that from the attacker's standpoint was you may need to calibrate multiple times until you guess. So for example, on-die termination is one of the things that we've explored. On-die termination is an option you can specify in the DIMM, and for most manufacturers there's either one option or there's up to maybe 5 options for the on-die termination. So if you try to calibrate against the DIMM and you're outside of the available window for calibration, you may need to change your own assumptions about what the on-die termination is and try it again, because that's one of the values that we can't read out, but we can certainly test multiple options.
Okay, thank you.
There was a question up front. I didn't quite catch it. Could you try it again or go to a mic? Sorry.
My question is, why not building a new RAM on
question was, why don't we build a DRAM module and sniff that one rather than go through the pins of an existing one? The attack that we were interested in exploring was something similar to like a traditional cold boot, where you encounter a system and you want to know what's the contents of that memory right there at this time. So we assume in the attack that we haven't pre-staged any kind of interposers or sniffers on the system. We just encounter it, somebody left it there, or we got access to a data center, and now is our opportunity. So we need to attack the system as we find it. Does that answer your question?
We really wanted to make as little changes to the victim system as possible. So in theory, yes, you're totally right. And in fact, we could have a physical interposer that sits between the DIMM slot and the DIMM. And that would make our lives so much easier. But we really want to say that we have a victim system that we just found, and it's turned on and it's in S3. What can we do with it? If that is the threat model that we use, at least.
So could you use the freeze preservations, freeze the module, take it out, put the interposer in, put the module in, read it, freeze again, replace the module?
We have actually tried that, but it doesn't work that way, because every time you remove the DIMM, the state that the DIMM was at is completely random, and you need to start from the beginning. If you look at the JTAG spec, it has a very complicated state diagram, and the moment that you take it out of the system, it's in undefined state, and you basically need to do the very same thing. It doesn't provide anything more than that you have already. And another point is the moment that you remove the DIMM from the DIMM socket, then it doesn't have power. So you might have some memory degradation there. In our attack, you don't have that, as long as you do the refreshes.
I was wondering if you considered the effect of ECC RAM and how it corrects into any memory corruption from your attack. Would it have any effect? Or have you considered that?
Not really, and because ECC doesn't really work that way, it works with different kind of, when you have external factors that make your contents corrupted somehow, yeah. But we can be the normal system that is doing reads and writes.
Okay.
So it shouldn't make anything, make a difference.
Thank you, everybody, for coming, and thank you for being interested in this topic.